In this video, we aim to provide a more detailed overview of the Poses tabs. While we have previously touched upon poses in earlier videos, this video will explore a more complex situation. We start by duplicating the station and renaming it into Robot. Then we open it in a 3D window and exchange the graphics of it with a Comau robot. Then we insert an instance of the robot into the frame. Now we insert a source and a conveyor and connect it with the station. We now start the simulation. As observed, the part is just animated on the robot and then advanced towards the conveyor. This is due to the robot being based on a station and just having a distinct graphic. Consequently, it functions like a station. To address this, we need to establish controls and poses. To do so, we reset the simulation and navigate to the Poses tab. Here, we can generate a new pose, which we'll name Pick. We can generate poses because we replaced the graphics of the station with those of the Comau robot, stored as an S3D file. S3D files contain a pre-kinematized graphical structure and already have defined joints, allowing us to utilize them for creating poses. Notably, each joint we wish to move can be individually selected. Upon selecting the desired joint, we can use the mouse wheel to preview the pose. Our goal is to create a pose where the robot picks up a part. As you can see, it might be hard to define the exact position when creating a pose. We can overcome this by defining the pose interactively. To do so, we first show the pose. Then we can pick the cone and drag it to a desired position. Now it is easier to move the cone interactively. However, keep in mind that in this particular scenario, we have a 6-axis robot with all joints activated in the given pose. For this configuration, we can compute the inverse. The supported configurations are detailed in the help documentation, as we have demonstrated in the video of the Pick and Place robot. This enables us to interactively define the pose. Once the pose is finalized, we proceed to create a second one, where the robot places the part onto the conveyor. Subsequently, a pull control is created. Within the pull control, we initially move the robot to the pick pose. Then we unblock the part. Post-unblocking, we wait until the part is on the robot to account for potential interruptions preventing the part from reaching the robot. We insert a wait until statement, where we wait until the location of the part is at the robot. It is crucial to review the comments at this point. As indicated, the anonymous identifier will be void after unblocking. Hence, it is impractical to use it further. Instead, we should utilize the forward blocking list. If you are unfamiliar with the forward blocking list, consult the help or refer to video 13. Thus, we create a variable named mu and assign the first entry of the forward blocking list to it. We then replace the anonymous identifier at with the variable. This ensures that the part is on the robot, allowing us to move the robot to the second pose. Once the robot reaches the pose, we can then move the part. Now we can save our changes. Then we deactivate automatic processing. The reason is that the time until the exit of the part is not defined by a fixed duration, but rather by the movement of the robot towards the target. If we were to neglect this adjustment, an exit event would be computed, triggering the part to exit prematurely. This is not our intention. We prefer the part to exit only when the robot successfully reaches its destination. Now we can run the simulation. However, it is not necessary to use poses exclusively for moving the robot to a specific position. We can also use SimTalk to move the robot according to our wishes. So we again look in the pull control. Initially, we remove the code section responsible for moving the robot to the pick pose. Subsequently, we can simply utilize the move to coordinate method. This method requires two parameters. The first is the coordinate to which the robot should move, relative to its position in the frame. For the first parameter, we enter the position of the source. The second parameter is another array, representing the rotation angle of the animation object around the specified axis. In our scenario, the rotation is unnecessary for picking the part, so we set the z-coordinate to 1. Now we can commence the simulation. As observed, the robot moves to the source, picks the part, and then transfers to the conveyor to drop it. However, our current approach is not yet robust, as we are relying on absolute coordinates. Our goal now is to enhance the code's resilience to changes, starting with the first parameter. What we want is that the robot moves to the part that he needs to pick by determining its position rather than using absolute coordinates. We have already determined the first part and stored it in the variable mu. We now replace the first parameter of the method by using the position attribute of the part. However, before accessing the position attribute, we need to access the 3D attributes, since the position is stored in the transformation dialog. Then we insert a breakpoint in the line, save our changes and start the simulation. Upon reaching the breakpoint, we press F10 to evaluate the expression. Then we notice that the coordinates of the variable do not align with our expectations, and the robot also moves to other coordinates than expected. This discrepancy arises because the shown coordinates are relative to the source rather than to the robot. You might ask yourself why the x-coordinate is at 0.5 meter and not at 0 meters. The reason for this can be shown when we open the source in a 3D window. Here we see that the booking point of the part is at 0.5 meter. Now we return to the model frame. Here we can now delete the first parameter of the method. To resolve this discrepancy, we can use the getPositionOfObject method. This method will determine the position relatively to the caller of the method, which in our case is the robot. To do so, we create a variable named pickPosition. First, we access the robot, then the 3D properties, and use the getPositionOfObject method. The first parameter of the method is the object whose position we want to query. So we use mu as the first parameter. Optionally, we can add an offset as a second parameter. Since we want the robot to pick the part from its top, we should include its height as an offset. To achieve this, we need to access the height of the part. So we can right-click on the part in the toolbox and choose Show Attributes and Methods. Next, we can input the letters M and U. Subsequently, we will observe that the part possesses an attribute named MUHeight. Then we can utilize this attribute as the z-coordinate for the offset. Following that, we assign the variable pickPosition as the first parameter of the method. Now, let's examine the second parameter, where we can make further improvements. In our current scenario, this parameter is not of relevance, since it determines the rotation when picking the part. However, let's consider a scenario where we have a tilted source. To illustrate this, we open the Edit 3D Properties dialog of the source. Subsequently, we set the rotation axis to Y and introduce a rotation of 60 degrees. Then we increase the height by 1 meter. In such instances, complex calculations would be required to ensure that the animation object picks the part at the correct angle. However, there is a simpler alternative. We can create another variable, which we will name MURotation. Then, we once again access the robot as we aim to obtain the rotation relative to the robot and proceed to the 3D attributes. At this point, we can invoke the getRotationOfObject method. This method takes as a parameter the object whose rotation you want to query. Now, we can employ this variable as the second parameter for the MoveToCoordinate method. Now we place a breakpoint at the next line, save our changes and let the simulation run. As you can see, the robot perfectly moves to the part and also considers its rotation when picking it. Now let's consider the placing pose. We can once again explore an alternative approach to the poses. Here the task is to determine where we should position the part. To accomplish this, we create a variable, which we will name drop position. The challenge at this stage is that we lack information about the part's placement on the conveyor. To address this, we follow a similar approach as before by opening the attributes and methods of the conveyor and searching for a suitable attribute. Even experienced users may not know everything, so they essentially employ the same strategy. Since we are seeking a method related to 3D properties, we can choose 3D at the top. This filters the view to display only the 3D attributes and methods. Upon scrolling down, we discover the methods getMU animation position and getMU animation rotation. Of particular interest is the getMU animation position method. Upon inspecting its signature, we note that we can provide either an absolute or relative position as a parameter. We can easily copy the method from the dialog and then assign the return value of the method to the variable. Initially, we access the station and then navigate to the conveyor through the successor attribute of the station. Subsequently, we paste the code. Next, we need to provide the parameter, and we are interested in the relative animation position 0, as we intend to place the part at the beginning of the conveyor. When using a relative value, a range between 0 and 1 can be passed. Alternatively, an absolute value with the corresponding unit can be provided. For additional details, you can always refer to the help by clicking on the method and pressing F1. Now, we will once again place a breakpoint at that line and allow the simulation to run to observe the return value of the method. As observed, the returned array represents the drop position relative to the conveyor's position. However, what we are seeking is the drop position relative to the robot. So this variable rather provides the offset for the drop position as needed in the move-to-coordinate method above. Therefore, we rename the variable to offset and create a new variable named drop position. What we should also consider is the length and height of the part. In the current state, the robot would position the part at the coordinate 0, 0, 1, but this does not account for the length and height of the part. Therefore, we need to make adjustments in the offset. To achieve this, we simply access the z-coordinate of the variable and add the height of the part to it. Then we want that the part is placed at the beginning of the conveyor, so we access the x-coordinate and then subtract the half of the length of the part. Now we reuse the getPositionOfObject method from above and assign it to the variable drop position. Then we replace the first parameter. Since we aim to drop the part at the successor of the robot, we can simply use a question mark and the suck attribute. As for the second parameter, we can now employ the offset variable. Then we insert a breakpoint and let the simulation run. When the simulation reaches the breakpoint, the values are not yet evaluated, so we need to perform a step by pressing F10. Following this, we can observe that the coordinates are as expected. Now, we can once again use the move-to-coordinate method from above to move the robot to the desired position. We then replace the first parameter with the drop position variable. For the second variable, we can use the coordinates 0, 0, 0, 1. Now the simulation is set to run. We remove all breakpoints, save our changes, and start the simulation. As you can observe, the robot is now picking and placing parts as intended. Now, let's summarize what we have accomplished so far. Initially, we duplicated the station class and subsequently replaced the graphics. Following that, we inserted an instance into the frame. Defining poses on this instance was a logical choice, considering that poses generally depend on the specific instance, and the coordinates are specified relative to the respective objects. However, as our work progressed, we made the decision to generalize the poses using Symtark code. This shift allowed us to move away from using absolute coordinates and poses and instead work with anonymous identifiers and methods, making our code context independent. Consequently, it might be beneficial at this point to consider utilizing our instance as a class that can be reused. To achieve this, we drag the instance to the user objects folder. However, by moving the instance to the user folder, it still inherits from the original robot class, which we want to prevent. Therefore, we cut the inheritance. Additionally, we can delete the original robot class since the new one is no longer inheriting from it. Following that, we can simply right-click on the class and select Save Object as. You might have noticed our variable gymnastics creating, renaming, and sometimes deleting variables. That's just us showing how even technology-savvy folks like us, trying to be the puppet masters of robots, don't always get it right the first time. We don't have a crystal ball for coding. So like everyone else, we dig into the online help and the secrets hidden in object attributes and methods. So an additional takeaway from this video should be that knowing where to find help is like having a robot sidekick in the world of programming. It is indispensable and sometimes unexpectedly funny. With that said, our video on poses and pick and place operations is concluded.